So, and then you are just having, again, rather low resistive state. And the same happens also into the negative. And of course, that was after we had measured that. This is not a prediction, it was an explanation of the data we have. So practically, we get a PZO. It's a bit thicker. It's at the limit of the tunneling. That's fine. It's at the limit of the tunneling. So, but thinner than that, it's tricky, because the PZO is a tricky material. Anyway, so we start measuring, and we went exactly here. So where we have a high resistive state, and then at a certain point we get abruptly into the low resistive state, and then we stay in this low resistive state until the ferroelectricity goes back down. So, and then you see here the values. Yeah, we are speaking about 10 amps per square centimeter, which is a massive current. It's a real massive current. And then you compare with 10 to minus 6, 10 to minus 5 on average. So it's the maximum what we have got was 10 to 6, even 10 to 7 on some devices, PER. So that means 10 to 8. But again, you see, at the remanence, we don't have that value. It's a very, very little remanence because we don't have polarization. It's a very tiny polarization. So the only thing we have is this. This resembles with a special resistive switching device when you put bipolar resistive with unipolar resistive. So it looks like the people doing resistive switching, they like this type of device just to prevent crosstalk. We were thinking that that's direct tunneling, and that is just Fowler-Norheim. It's just when we put polarization into the landscape, that lowers basically the barrier, and we enter automatically into the Fowler-Norheim regime. So remember this one. So that was by applying a voltage. Now at a certain voltage, so we have polarization, we don't have polarization within very, very little amount. It's popping up the switching. So practically, so that values are coming from the fitting we've been doing, which was decently good. So you see that we have 2 and 1 EV, and then polarization pops up, and then the drop is about 1.5 EV, 1 EV. It's a massive drop, which obviously, if you apply a certain voltage, which is about 1 volt or 1.5 volt, that is even thinner here. That goes even down. So it's why you are just onsetting automatically the Fowler-Norheim tunneling. So practically this very high electron resistance effect, that comes from changing the transport mechanism. So from the tunneling to the Fowler-Norheim tunneling. So as a summary, so I hope I managed just to convey to you a number of effects which are still happening at the interface, a ferroelectric metal interface, and which can be studied nicely using this tunneling and then tunneling spectroscopy as well. I think it's worth still going on it. There is a lot of physics in, like this PZT, so we have data now that only PZT does change the TMR. So all ends, so zirconium titanate and lead titanate, they do not. So why is that? We have absolutely no clue. And that's outlook. So we just to show you that we want just to do a step into the device, and then we have started just to transfer those few nanometer devices, so something like 5 nanometers, 3 nanometers, to silicon, or even to plastic. So that's a fully functional tunnel junction transferred, which was about centimeter large, transferred on polyethylene tetrafluoride. Not poly, whatever it is, PET. So the one we use for water. Yeah. So and it's really working after really device transferred on. I will not show you how, but that's still under patenting now. So thank you very much for your.
Thank you very much, Marin. So please, do you have any question?
Hello. I was wondering how metallic is your LSMO, and should you, if it is on the verge of ending from semiconducting to metallic, should you also worry about the depletion region that you may be creating?
The Curie temperature is just at room temperature. It's about 323, 300, something like this. So we've measured also the magnetization and also from the resistance versus the temperature, you get exactly this. Then you get into metallic state. So we've measured all the way down to 4 Kelvin. So it's is no problem.
So okay, so it's not a P-type semiconductor.
So yeah, TMR is not very good measurable at room temperature because the magnetization is rather low. So you have to go at least 70 Kelvin.
No, in that case, it's still P-type because it's marginally metallic, so it's a poor metal. It's yeah, it should be treated as a heavy doped semiconductor.
Yeah, but it's a bad metal in the sense that it's a spin-dependent transport within E, so LSMO. So if you have a spin in a spin direction, it's opening or it's closing the path. Yeah.
Thanks for the beautiful talk, Marin. I have a question, or 2 questions in one. First of all, I think I missed, what is the exact makeup of your PZT? Is it 2080 or?
It's 2080, yes. So I didn't mention it was written there. It's 2080, yes.
Okay, and that kind of goes into my second question. So you say that the 2 pure N members, PTO and PZO, don't have this very large response. Have you kind of explored also even closer to the MPB, to what you think is the sort of softening that's leading to these large?
Yes, we did, but unfortunately, so at MPB, so the compositions at MPB do not grow nicely. We didn't manage actually just to get perfect films. So and then we have somehow discarded the results as being unreliable. So, but let's say some devices are switching, some devices are not switching. So I cannot say is fundamentally switching or not.
Last question.
Do you have any theoretical support for the change of the barrier height between antiferroelectric and ferroelectric states?
No, I don't have any theoretical support. I mean, so the theoretical support is the one, let's say, based on the influence of polarization on the band alignment. Okay, that's the only one which I have. So whatever theory is there, whether it's microscopic, is nanoscopic, or ab initio, that's the only one. So we've been looking into this, but only for Schottky diodes, and we have taken actually polarization as a fixed charge at the interface. Only, but we did that something like 15 years ago, looking into the leakage in PZT. That can be a mechanism.
Just a quick question for when you are in solar node, for the